Okay, one more thing and then we're done. We have been working with this top formula right here. A confidence interval for the mean is given by the sample mean plus or minus a critical number times the standard deviation of the population divided by the square root of the sample size. This does depend on the assumption that we know the standard deviation of the population, and we'll give a formula that doesn't make that assumption a little bit later. There is one other confidence interval that we can do right now with really almost no more work at all, and that is for proportions. For means, you have to have some kind of a numerical measure, like you're weighing a bunch of different bobcats, and you can take the mean of those, and then you can give an estimate for the mean weight of the entire population. You can do this for proportions as well. For proportions, these come from the kind of measurements where you're doing counts. A person has a certain characteristic or they don't. Or in quality control, you're looking at parts coming off from an assembly line. This one is satisfactory or it's not. So when you start working with counts rather than by measuring something, then you're on to proportions, and it turns out that there is a formula for confidence intervals for those as well. And I'm going to show you with an example how to use this second formula, and it turns out it's not a lot different from what we did for means. Okay, for a community college, we want to ask the question, what proportion of the students are female? And in order to try to get an answer to that question, we take a random sample of 50 of those students, and we find out that 31 of those 50 are female. We would like to compute a 95% confidence interval for the proportion of females in the whole population, and we'll get that estimate from the proportion of females that are in the sample. All right, we want a confidence interval for a proportion, and we saw in the last slide there's a formula for that. It's P with a hat over it, plus or minus Z star or ZC, you could say, times the square root of something kind of big, P hat 1 minus P hat over N. As before, N is the size of the sample. Z star, that's the Z critical value, the very ones that we were using for means. And now what are these P hats? Well, here's the idea. As before, we have a whole population. There is a proportion P of that population that has the characteristic that we're interested in. In the case that we're looking at right now, we're going to say that that characteristic is that the person identifies as female. Now, you can take out of that population a smaller sample, and you'll have a proportion of this sample that identifies as female, and that is also, we kind of want to use a P for that to mean proportion, but it will be confused with this one if we don't do something. So what people do is they put this caret character over the top, and that is generally read as P hat. It's just a quick way of saying what's on the page here. So a 95% confidence interval would be obtained this way. You look up the 95% critical value. You might remember that's 1.96. And then you take the P hat from the sample, put it here, plug it into here along with the N, which is the sample size, crunch the numbers, and you've got your confidence interval. Now in the example we want to do, we have a sample size of 50. 31 out of the 50 have the characteristic we're interested in, and that is exactly 62%. And we would like to use our formula here to get a 95% confidence interval. Okay, 95% confidence interval. We're going to do that first of all by starting with our point estimate, 0.62, and then we add and subtract the Z critical value, And if you've forgotten, that is what we get out of our table. Down here at the bottom, we're looking for 95%. That Z critical value is 1.96. And then we need this stuff under the square root. You start with p hat, that's 0.62. And then 1 minus p hat. And you divide by the square root of the sample size. We had a sample of size 50. This is the point estimate. Once again, this thing right here is called the margin of error. And now we're ready to do our calculation. So let's get that margin of error. 1.96 times the square root of, and what goes inside of here is 0.62 times 1 minus 0.62 divided by 50. And so the margin of error is plus or minus, let's round this off to 4 decimal places, so 1345. And that's being added and subtracted to the point estimate of 0.62. So if we take 0.62 and we add 0.1345, we'll get 0.7545, and we could have subtracted it as well. So let's go back to entry here, change that to a subtraction, and we get 0.4855. So what we're saying is that we are 95% confident from this sample alone that the true proportion of female students at this community college is between 48.55% and 75.45%. Now, what if we wanted to narrow this up? Let's take a look at this thing right here. This margin of error just now is a little bit bigger than we'd like. That's 13.45%. Maybe we'd like to be able to estimate, say, to within plus or minus 5% or something like that. Well, our margin of error is this number, 1.96 times 0.62, and let's just convert that. 1 minus 0.62, that is 0.38 times 0.38 over n, which is 50. That right there is 50, and we have the square root of all of this stuff. And currently, this thing is equal to 13.45%, 1345. Okay, now, what we can do, if we'd like this number to be smaller, we could increase this sample size right here. So let's put an n in there. And then I'm going to put this as the same. So let's assume that our sample proportion were to remain the same. But what if we said, well, you know, we really would like this to be plus or minus 5%. So we can just plug in what we want here, and we can solve for n. Now you have a couple of different possibilities here. You could just guess and check, and eventually you'll find an n that'll work. But there's really a little bit easier way than that. How about if we divide each side by 1.96, and why don't we multiply this out here so we don't have quite so much to work with. Using a bit of algebra, we've got 1.96, and then if we have a over b and take the square root, that's the same as taking the square root of a divided by the square root of b. So we're going to take this product right here, which is 0.62 times 0.38. That product, 2356, is that number right there. But I want its square root. So I'm going to take second square root of that previous value. That did not work. Second square root of 0.2356. And I get 0.48. Let's round a little bit, 0.4854. And underneath, I'd have the square root of n. And I want this whole thing to be equal to 0.05, or if it turned out to be a little less, that would be okay as well. Okay, now in general, if we have a fraction, say an a over a b is equal to c, and you're trying to solve for this b down here, what you do is you take the reciprocal of both sides, and then you can multiply through by the a, and you'll have your b. So that's what we're going to do here. Let's get that copied over. We may as well multiply this out. That'll save us a little bit of work. So we have 1.96. Well, actually our number, 4854, to full accuracy, is right on the screen already. So let's just multiply that by 1.96. And 95136 is what's in the numerator there. That's in the numerator. Root n is in the denominator, and 5% is our target margin of error. So we take the reciprocal of both sides. And then we multiply each side by this denominator. The square root of n is 0.95136 divided by 0.05, squaring both sides and computing this number here, 0.95136, etc. Divide that by 0.05. That's our number. It's about 19 right here, and then we have to square both sides. So we're going to square that. So take the previous answer, raise it to the second power, and we get 362.03, which is to say it takes us about 362.03 people in our sample to guarantee a 5% margin of error if the proportion were to stay the same. Now, of course, you can't get 3/100ths of a person. So this means that n must be 363 or larger in order to get a margin of error of 5% if our 62% remains the same in the following samples. Now, you might be wondering this. Let's go back and look at that margin of error again. That is z star times p hat 1 minus p hat over n, take the square root, and then we have a target for this margin of error. Now, we could solve this for n just as it stands. And if we did, what we would do is probably something like this. Let's take me divided by z star. And then we would, once we divided by z star, we just have the square root on both sides. So we're going to square both sides. And we'll have p hat 1 minus p hat over n. Then you could take the reciprocal of both sides. Z star over your target margin of error squared is equal to n over p hat 1 minus p hat. And then to solve for n, you simply multiply through by this denominator. P hat 1 minus p hat z star over the target margin of error all squared. And you can use this without doing the algebra. So if that algebra seems a little intimidating for you, there you are. There is the how to get the sample size to get a target margin of error. This is when you have an estimate of p, which is p hat. So if we think we know approximately what p is, call that estimate p hat, plug it in here, plug in your target margin of error, and you're good to go. Now there is another formula that you can use as well, and it turns out that this part right here, this p hat times 1 minus p hat, this is as big as it can be when p hat is equal to a half. If p hat is equal to half, you get a half here. 1 minus a half is a half again. A half and times a half is a quarter. So it's also true to say that it won't be any worse than this. And this is in fact the formula that most people would use. So that way I don't have to depend on the answer coming out to be anything in particular. I just know that if I use this for my sample size, I'm guaranteed to get my target margin of error. So let's go back. And I got my inequality going the wrong way. This should be greater than or equal to. Let's go back and repeat this. What if we want a margin of error of no more than 5%? Then we would say this. You plug in a quarter. At 95% confidence, that's 1.96. Margin of error is 0.05. And this then becomes a pretty simple calculation. I take 1/4 or 0.25 times 1.96, and I need to open my parentheses there, which I've already got on the screen. 1.96 divide by the target margin of error, which is 5%. I want to square that, and I come up with 384.16. And so we should use n equals 300. You can't get 16/100ths of a person in your sample, so you're going to have to go up to 385, and that's how you can predict the sample size that you'll need in order to get a target margin of error. Well, that is it. Congratulations. You have made it through the introduction to confidence intervals. I want to say thank you to those who have stuck with me. You have crossed the boundary, not only the boundary that separates those who know something about confidence intervals from those who don't, but you've also crossed into the territory of inferential statistics. If you will put the effort in right now, and I know that some of this can be a little bit hard to learn, but I am telling you from long experience that if you put the effort in now to really understand what's happening with confidence intervals for the mean and for the proportion, you get good at using the tables, you get good at using the calculator, this is going to pay just huge dividends for you, and it's going to make the rest of the course so much easier. So thank you for sticking with me. Congratulations on getting this far, and I'll be seeing you again soon.